Starting the new article, different cases of AC circuits. In this particular topic, we are going to understand about different kinds of AC circuits. So, I am starting with the first AC circuit with only resistance. So, whenever you find out such kind of AC circuit that are only with the resistance, so in this particular AC circuit, the inductor and capacitors are absent and the resistance is only present, and so the voltage will be only applied to this kind of circuits. And now let us see the arrangement of such kind of AC circuit. So in this figure, as you are watching, that only resistance is given, whereas the inductor and capacitors are eliminated, and the voltage which we have applied on the introduction theory, the same voltage we are applying over here. So we have studied about the impedance, that was Z is equals to R plus J into omega L minus 1 upon omega C for LCR circuit, but here it is only R circuit. So this quantity will be 0, because there is no presence of inductor, as well as this particular quantity 1 upon omega C will also 0. And so the value of impedance is the same as the value of resistance in the case of AC circuit with only resistance. And also if you want to find out its magnitude, then it is also under root of R square, that is equal to capital R. Now here the value of delta, if you want to find out, so from the equation of tan delta, that was omega L minus 1 upon omega C divided by R, but the numerator is 0, so 0 over R is 0. So whenever this tan delta is 0, only when the delta is equals to 0. So there will be no phase difference. And if you want to find out the current passing through this AC circuit, then we have the equation I is equal to voltage upon impedance. Therefore, the current I is equal to voltage is Vm cos omega t divided by the impedance Z is now equal to R. So this is the value of current. Now let's study the characteristics of voltage and current with respect to time in such kind of only resistive circuit. So here, as you see from the figure, the voltage and current are taking on the same line or same axis, and on the x-axis we have taken the time with the frequency. So here the voltage is having the larger value than current, but the phase difference between voltage and current are 0, because they are moving parallelly to each other. And here in the AC circuit with only resistance, the phases of voltage V and current I are equal. And now we will see the another kind of circuit with only inductor now. Let's move to the different case of AC circuit. Now that is with only conductor. So as far as the above case was concerned, here the resistance R and the capacitor C will be absent, and only inductor L will be present. And now the effect of voltage will be only applicable to this inductor L. So let's see that how does the circuit look. So this is the circuit or AC circuit with the use of only inductor. Now if you see over here, on the value of impedance, that is Z, is depending on the value of L only. So the effect of R and minus j upon omega c will be 0. So now in this case Z is equals to j omega L. And now if you want to find out the relation of real axis and imaginary axis, then the relation is look like this type as shown in this figure. This is imaginary axis and this real axis. Now I want to find out the magnitude of this Z. Then the magnitude will be only omega L, that is equals to the value of XL. And here if you see, the imaginary axis is on J and the real axis has no values, and so the phase difference between imaginary axis and real axis, that means here the value of delta is directly obtained from the relation between real and imaginary axis, that is both are perpendicular to each other, and so I have the value of the current flowing inside the AC circuit with only inductor is Vm into cos. Now there is a phase difference of pi by 2. So I have to minus this pi by 2 distance from the omega t, and that is divided by the value of z. Here the value of z is the magnitude of z, that is equal to omega L. Or you can write down in this way, I is equal to Vm cos omega t minus pi by 2 divided by the omega L is also equal to HL. And now we will show the effect of voltage and current with respect to time. So here there is an effect of voltage and current with respect to time, and you can see the phase difference between the legs of voltage and current, that is pi by 2. And so I can write down one statement that current, see this dotted line is for current and this darkened line is for voltage. So current is lagging behind the voltage in terms of phase by pi by 2, means by 90 degree. So we have performed the AC circuit with R only. We have also performed the AC circuit with L only. Now we will see the AC circuit with only capacitor. Let's move to the third case of AC circuit, that is now with only capacitor. So obviously here the inductor and the resistance will be absent, whereas capacitor will be present, and also the impedance will be now depend on the value of only capacitance. Now let's see that how does the circuit look. So here is the circuit of AC type, that is now only with capacitor, and here if you want to find out the impedance, means Z. So now Z will be of minus j over omega c, and that implies the magnitude of Z is given by 1 over omega c, that is xc. Now as this capacitor is now only in the z-axis or in the z impedance, so the relation between the real axis and imaginary axis of impedance are given by this kind of figure. So here the real axis and imaginary axis are also separated by the phase difference, but now here the phase difference is in the negative axis because of this value of z1 over omega c, and this is point OF is showing the distance 1 over omega c, and the phase difference is minus pi by 2, and here also there is absence of the real part in the case of impedance z. And now I can write down the value of current, that is voltage divided by impedance. So here voltage is equal to Vm cos omega t plus pi by 2 divided by the impedance, that is 1 over omega c. And with this we have find out the value of current. So what kind of relation we will get according to the nature of voltage or current with respect to time interval omega t. So let's find out the relation. So here there is a relation between voltage and current and the time interval, and as we are knowing here the opposite effect from that of inductor we are observing. The now current is leading. In the previous case the current was lagging from voltage, but now here the current leads the voltage in terms of phase by pi by 2 angle, means 90 degree. So this kind of graph is totally opposite to the graph of AC circuit with only inductor, and such kind of relation we are obtaining in the AC circuit with only capacitor. Now we will see some different combination by joining RL and L and C, and then we will see the L and R kind of, or C and R kind of combinations. But first of all I am starting with R and L, which are joined in the series. The fourth case of AC circuit is now by taking the R and L combination connected in series. So here R plus L is present and the capacitor C is absent, and such kind of arrangement is look like this figure. So here L and R are connected in a series. So here the value of impedance means Z is equals to R plus J omega L, because the value of minus J over omega C is cancelled out because there is absence of capacitor, and so the magnitude of Z is under root of R square plus the value of omega square L square, that is equal to under root R square plus XL square. So this is the magnitude of Z, and as here the Z is consisting of real part as well as the imaginary part, so it is necessary that we should study about the characteristic of this real and imaginary axis. So here the relation between real axis and imaginary axis is shown. This is the imaginary axis and this is my real axis, in which the value of OD is given by R and the value of OA, that is very equal to HD, is equal to omega L, and from which I can find out the value of mod Z. So that will comes out to under root R square plus XL square. But what is the actual value of tan delta? Because our aim is to find out the phase difference and then to understand the characteristics of the given case of circuit. So here the value of tan delta is OA or HD over OD, that is equal to omega L over R, and from this I can find out the value of delta by getting tan inverse on the right hand side. So delta is equal to tan inverse omega L over R. So we have to find out the characteristics of voltage and current with respect to time interval, but we are not at present know the value of this inductor L, and so we cannot judge the characteristics of voltage and current, but we can assume that the nature of that characteristic. And so in the characteristic of voltage V and current I with respect to omega t, this characteristic is of the current lags behind the voltage in phase by the phase difference delta. And here if you want to find out the actual value of current I, that is given by Vm cos omega t minus delta divided by under root of R square plus omega square L square, because here current lags behind voltage and the value of delta is not known at the present. But whatever the value of delta comes in your calculation, you can directly put in this equation and you can judge the value of the electric current that is passing through the circuit. So this is all the analysis about the AC circuit with resistance and inductance, and in the value of current is also independent of the value of capacitor.